Hello everyone. In this video today we're going to continue with the cruise stage of the flight. So in the cruise usually we have two major questions. So both of these questions originate from the fuel that we have on board. So the first question is during the planning stage, or even for the management of the airline company, would be from a given amount of fuel, how far can we go? So how far can we go? And this would usually be a distance on the ground, right? So a distance on the ground. We're at Nyíregyháza, we have a given amount of fuel on board with a given type of aircraft. How far can we go from here? Or when they're planning the Wizz Air flights, for example, right now from Budapest when they go to China. Of course, this is also a very important question, like how far can we go from a given amount of fuel? So when do we need to stop for fuel if we want to get from Hungary to China with the given amount of, or with the given type of airplane? The second important question would be, how long can I stay in the air, or stay airborne? It basically means the same thing. So what is the amount of time that I can still remain in the air? For this, the example would be, for example, you arrive to your destination aerodrome and the weather is pretty bad. So you're entering what is known as a holdings somewhere in the vicinity of the aerodrome. So you're basically waiting for the weather to improve so that you can do your approach and land the aircraft at your destination aerodrome. And the question at that point would be, how long can I stay airborne? And this would be an important question also for the air traffic control unit services, if you think about it, because if you have a whole bunch of airplanes waiting in the vicinity of the aerodrome, which one you land first? Of course, there's also like a priority in arriving, right? So in order of arrival, but safety is more important, right? So if somebody shows you that they're low on fuel or they have lower endurance, of course they would have to let them first. So it's an interesting question, like how long can you stay airborne? Okay, so in aviation, how we call these two, what we answer these two important questions with, the how far can we go, or how far we can go, is basically going to be given by the range of the aircraft, and the how long can I stay airborne is going to be the so-called endurance of the aircraft, right? And we're going to start today with the range. So first is going to be the range. We're discussing the range, and after that we're going to be discussing the endurance. Okay, so the range, by definition, by simplest kind of definition, is the distance that can be covered, or that can be flown, covered, let's use covered, on the fuel available on board. So is the distance that you can cover with the fuel that is available on board. So there's gonna be two types of ranges. Yet again, is a distance. So range is going to be essentially a distance. So there's going to be two kinds. So when you would plan a flight, in the flight planning stage, you would look, for example, you're in Hungary, for example, try to draw the best Hungary that I possibly can, and you're taking off from Budapest, and you're going, for example, all the way down to Cyprus. Going down all the way down to Cyprus. Right. So you plan this flight on the map, right? So it's a two-dimensional image on the map. So of course there's a whole bunch of other countries in between. The point is that you're usually going to be taking off. You go to a point, you go through other countries, you go through a whole bunch of points, and you end up landing at your destination. So what you do is measure these individual distances and you add them up. Right? So you measure these individual distances and then you add them up. And then you receive a distance. And we call these distances measured on the ground. So this would be a ground distance. And we measure usually the ground distance in what is known as nautical ground mile. So it's basically nautical miles measured relative to the ground. Right, and initially this is what we're interested in. So we want to fly from A to B, and I measure the lengths of the different legs on the chart, and this is going to give me a nautical grand mile, right? And of course I'm going to have, so this is the first type, a ground range of the aircraft. And these are the two ones which we need to measure together, like the ground range of the aircraft. Can it cover the ground range or the ground distance from the A to B flight, right? So these distances, can it cover it? If it can, of course, you can fly to this aerodrome. It's still within your ground range. But in reality, the airplane is not flying, or basically is not flying on the ground. It's flying in the air, right? And the air mass, so the aircraft is within the air mass, so this mass of the atmosphere, it's made up of the air particles all around, and the airplane is flying within that. It's flying within this air mass. However, this air mass too moves relative to the ground. So the aircraft usually flies a distance within the air mass. However, based on the type of wind, in this case we show that the aircraft is moving from left to right relative to the mass of air, and the mass of air is moving on this little drawing from right to left, right? You can see that here. So it's a headwind component from the aircraft. So relative to the ground, when you add up these two motions, you would get something like this. So your displacement relative to the ground, so this would be the nautical grand miles, and this would be the nautical air miles. So the distance, so nautical mile measured or covered relative to the air mass, right? That's nautical air mile. And so therefore this is going to be an air distance. air distance. Is the motion of the aircraft relative to the air. And usually this is the one which we will be able to calculate initially, because this is only dependent on the aerodynamic properties of the aircraft, the type of propulsion, and basically the environment, or the functions, the variables of the environment, like outside air temperature, pressure, altitude. So therefore, usually the density, right, and also maybe the humidity. So we usually calculate first this air distance, which is also going to give us like an air range, and we compare it to the ground range, which is given by the planning stage. And we also call this ground distance or ground range. We also call this still air distance, because if there is no wind, if the mass of the air in which the aircraft is moving is not moving relative to the ground, in that case, the motion of the aircraft against the air mass is going to be the same amount relative to the ground as it is relative to the air. So in that case, the two would be the same, right? So the distance which the aircraft covers relative to the ground, it would be the same as the distance the aircraft covers relative to the air. However, there is always like some wind, especially aloft. Like even if it's almost like a calm wind situation near the surface, because of the boundary and the surface friction effect, aloft. So at higher altitudes, there's always usually some sort of wind, which is usually much stronger. And so therefore, in most cases, we cannot neglect, in almost all cases, we cannot neglect the effect of the wind. Okay, so when it comes to range, as we saw, there's going to be two types of ranges. So the first one is going to be the so-called air range, and is measured in nautical air miles. And the second one is the ground range, which is measured in nautical ground miles. Okay, so these are the two ones. So range is a very general term, and as you can see, it's highly dependent on the fuel available on board. So it's dependent on how much fuel you take with you. So in the general calculations or a general consideration, it doesn't really give us much information about the capability of the aircraft, or about the performance of the aircraft, I would say, right? So it's not giving us much information because it's heavily dependent on how much fuel you have on board. And this is the reason why we have developed or why we have expanded the definition of range a little bit. And instead of using simply the range, is going to be a definition known as the specific range. So specific range, so the next definition is the specific range, and by definition it is the distance flown or covered per unit amount of fuel. And this is more interesting for a given airplane, right? So it's going to give us from a unit amount of fuel, how much range can I cover? So it's a pretty good indication of the performance of the aircraft, right? Because if the specific range is high, it means that I can cover a big distance, a bigger distance from the unit amount of fuel. So therefore, it doesn't matter when I bring, little fuel or bring more fuel. Of course, it's going to affect the range, but the specific range should be pretty consistent. And you know, the better airplane would have a better specific range. And that's a caveat. If you have a little or lesser specific range, it means you might have to fuel more from that on that given airplane with a lesser specific range to get the same amount of range, which is going to cost a lot of mass. And as we have seen in previous videos and in previous classes, we saw that adding mass to the aircraft usually deteriorates the performance of the aircraft altogether. So it's better to have higher specific air range. So based on the type of range that we're talking about, the specific range as well, we can basically select into two categories. So there's going to be 2 times the specific range. There's going to be the specific air range. Specific air range is also usually we're going to index or shortify as SAR, which is measured again. Well, we're going to see the unit in a little bit, but it's going to be the nautical air mile per pounds or kilogram of fuel, basically. And we're going to have the specific ground range, which we're going to index as SGR, specific ground range. And the unit for this one is going to be nautical ground mile per pound or kilograms of fuel. Right. So in a general, as a general dimension, you would have the specific range. So this is neither air nor ground. This is just the dimension. So the dimension of the specific range would be nautical mile per kilogram, right? So it's the distance you can cover from the unit amount of fuel. So it tells you how many nautical miles can the aircraft fly from 1 kilogram of fuel, right? So what we're gonna do next is when we're gonna divide by time, both sides, right? So we're gonna have or multiply with time over time, or 1 over time over 1 over time, right? So it's basically multiplying with 1. So what we're gonna do is nautical mile over time over kilogram. Well, instead of time, because this would be dimension analysis, let's use hour. That will be the System International. Well, no, the System International would be the second, but let's use hours. So nautical mile per hour in kilograms over hour. Okay, so what we're gonna get. So nautical mile per hour is a distance. No, let's use another one. This one is a distance over time. What kind of physical measurement does that give us? What kind of a unit is that? Is a unit of velocity, right? And nautical mile per hour is the unit of knots, right? It's going to be knots. So it's going to be a velocity. A velocity in knots over, and kilogram per hour. So kilogram of fuel per hour is what is known as fuel flow. So kilogram of fuel per hour. And we're gonna index it with, well, not the dimension, but we're gonna index it with B. So this one is B, is known as the fuel flow. Okay, so what we have gotten, well, let's use brackets, so knots, and this one is kilogram per hour. So what we have gotten is that specific air range is going to be a velocity over the fuel flow. And so how we can take it further for the specific air range and for the specific ground range, this formula is that we're going to say that the specific air range is going to be, so what is the velocity against the air mass? So which one is the velocity of the aircraft which can be measured against the mass of air basically in which I'm flying? It's going to be the true air speed, right? So it's the true air speed. So it's going to be the true air speed over with the fuel flow. And this gives us back the initial dimension analysis which we got right here, is that the specific air range is going to be the true airspeed over the fuel flow. And on a very similar analysis, we're going to get that the specific ground range is going to be a velocity relative to the ground over with the fuel flow. So which velocity do we usually have relative to the ground, which takes into account the wind? Of course, is the ground speed, right? So it's the speed of the aircraft measured relative to the ground. So it's going to be the ground speed over the fuel flow. And this is their formula. So this is the formula for the specific air range, and this is the formula for the specific ground range. Okay, so let's talk about the fuel flow, which was the dimension for it was kilograms per fuel per hour. So generally speaking, we can say that this fuel flow, how we express it, is going to be a little bit different for the for the jet and for the propeller-driven aircraft. So we'll have to make two distinctions again here. So one is going to be for the jet, and the other going to be for the propeller-driven aircraft. Right, so for the jet, it's going to be proportional. So this fuel flow is going to be proportional to the thrust, which is generated. And for the propeller-driven aircraft, this fuel flow is going to be proportional to the power. Right, and the main function of this fuel flow is basically, one is the specific fuel consumption for the type of aircraft, and we'll see this in a short bit. So it's also going to be, in both cases, it's always a function of the specific fuel consumption of the aircraft. But I think it makes sense why, right? So how much fuel is flowing to the engine in an aircraft? So how much fuel is the aircraft consuming is going to be determined by the specific fuel consumption of that aeroplane, basically, of the type of engine. So better, more efficient engine, of course, is going to have a lower specific fuel consumption and a lower fuel flow. And if you look at it in the previous formula, if you lower the fuel flow for either case, you're going to get a higher specific range, which is going to be great because it means that for a unit amount of fuel, you're going to be able to cover longer, so bigger distance, so more nautical miles, which is essentially good. And a more outdated engine, a less efficient engine, would have a higher specific fuel consumption, so therefore a higher fuel flow. right? So is that what it means? And again, for the jet, this fuel consumption, this specific fuel consumption, we usually look at the thrust specific fuel consumption. And for the propeller-driven aircraft, we're looking at the power-specific fuel consumption. Okay, so the specific fuel consumption, so usually we say SFC, specific fuel consumption. So usually we use this specific fuel consumption. We like to use specific from everything, because you could say like my aircraft is consuming like 200 kilograms of fuel per hour. Is that good? Is that bad? It depends. If it's a little Cessna, it's probably pretty bad. But if you're talking about a jumbo, is probably not even enough, right? So so it depends. Like 200 kilograms of fuel consumption, it doesn't really tell us much. So this is why we're using the so-called specific fuel consumption, which is going to tell us for a jet, the thrust specific fuel consumption for the jet is going to be, so specific fuel consumption for the jet is the fuel flow, which we're also going to index as the jet, over the thrust. So how much fuel flow do I need to generate? How much fuel flow do I need to generate kilogram per hour to get a unit amount of Newton? And of course, the lower this is, so with the lower amount of fuel flow, kilogram per hour, I can generate the unit amount of thrust, the better. And this is independent of the size of the aircraft, because it's visible that the fuel flow, however, so if you want to get the fuel flow out of the picture, the fuel flow is going to be the specific fuel consumption for the jet times the thrust. So let's look at the example of, let's say, a teeny tiny 737 200. So it has this, cigar looking engine. It has this very cigar looking engine. And it's kind of small. It's kind of a small airplane. So it has a center of gravity. And it's going to have a given, little weight. So for the given amount of weight, it's going to need to generate a given amount of lift to counteract it, and it's going to, from the lift generation, generate a given amount of drag, and this given amount of drag needs to be counteracted with a given amount of thrust. But let's look in comparison, and I'll try to get the sizes maybe right. Let's look at a 747. Yeah, I'll try to get the shape of the nose right. And it's this very huge airplane. Right? I cannot stress, the size right here. And it's probably even like longer. It cannot even fit on the picture. It's that big. And these are like the same metrics used for both of them. Right, so it's going to have a center of gravity as well. And the mass of this one, or the weight, is going to be much bigger. So therefore it needs to generate a large lift force, and so therefore it's going to generate a larger drag, and so therefore it needs a larger amount of thrust to maintain it. So the thrust for this airplane is going to be much larger than the thrust generated by the 737. So the thrust for the 747, 747, let's say 8I, is going to be larger than the thrust generated by the 737-200. Right. So the thrust is larger, so therefore the fuel flow is going to be larger. Right? So if you want to compare them, so if the thrust of the 747 is larger than the thrust of the 737, what you're going to have is that the fuel flow of the 747, which is the specific fuel consumption times the thrust of the 747, is probably going to be higher for the 747 than it is for the 737, which is the specific fuel consumption of the 737 times the thrust generated by the 737. Right. So in reality, you can see that the fuel flow is going to be much higher. So it's going to require higher fuel flow to generate, this amount of thrust. However, since the specific fuel consumption of the 747 might be lower than the 737, because this is like the newest type of 747 engine, and is very high tech, very high bypass ratio engines, very efficient. So actually, it can so happen that the the specific fuel consumption of the 747 is actually less than the specific fuel consumption of the 737, which was very outdated, 200, mind you, with this very old, very nasty, very loud single bypass or single spool engines, basically. So in that case, the fuel flow is actually higher. However, the specific fuel consumption is lower than the specific fuel consumption for the 737. However, it can happen that the thrust is so much higher than that is required for the 737, the fuel flow is going to be higher. But that doesn't mean, if the fuel flow is higher, it doesn't mean that the 737 is more efficient than the 747-8Y. It just simply means that there's less fuel required, kilograms per hour, to generate this amount of thrust. Right? However, for the unit amount of thrust generation, the specific fuel consumption of a larger airplane might be more efficient. It just simply is required, more units of thrust to maintain straight and level flight. So if you multiply that by the thrust which is required, you're going to simply get a higher fuel flow. So by itself, the fuel flow doesn't give us a direct indication whether the fuel consumption of the aircraft is efficient or not. So this is why we use the specific fuel consumption. Okay, I hope that makes sense. And so again, to get back to our initial question, so this is why we're talking about the specific fuel consumption for the jet with regards to the thrust, and this is also known as thrust-specific fuel consumption in engineering. In the ATPL, you're not really gonna see it as such. It's just gonna be said that the specific fuel consumption for the jet is the fuel flow, which is specific to the thrust, so divided by the thrust. So again, a fuel flow, which is kilograms of fuel per hour, over the unit amount of thrust that it generates. And from this one, and this is a very important formula right here, is that the fuel flow for the jet is going to be the specific fuel consumption which is again dependent on the engine, right? So it's an engine dependent consideration, whether it's it's efficient engine, it's not so efficient, what's the bypass ratio, and so on and so forth. So it's a very complicated mechanical aspect, which we we take into consideration this entire mechanical process as a specific fuel consumption from our point of view, and of course times the thrust. And again, usually we also call this as the thrust required, and we're going to see later why that's important. And for the propeller driven aircraft is very similar. So for the propeller driven aircraft, so propeller driven, we're going to say that this specific fuel consumption for the prop is not specific, the fuel flow is not specific to the thrust, but rather the power, right? And so this fuel flow for the prop is going to be specific to the power it generates. And so if we express this, what we get is that the fuel flow for the prop is going to be equal to the specific fuel consumption of the propeller-driven engine. So is yet again is an engine consideration times the power it generates. And I'm not going to go through the whole detail like in the previous case, but it's the same case. So you might have bigger aircraft, bigger mass, bigger power required. So therefore you're going to need the bigger power available. So therefore you're going to need a higher fuel flow. And this is why we look at this specific fuel consumption, why we look at the fuel consumption instead of the fuel flow, because this is going to mean that a larger airplane is going to have a larger fuel flow, basically. However, still the larger aircraft can have a more efficient engine, so therefore the specific fuel consumption can be lower, and so therefore the specific fuel consumption, which tells us what is the fuel flow required to generate a given amount of power. And so this is what we're going to use for the propeller driven ones, and is the same exact logic as we saw for the jet, right? It's the same exact logic, and this is also from here a very important formula that we're going to use. And so for the turbojet engine, we can also say that this specific fuel consumption is the lowest, so is the most efficient, usually at lower air temperatures, and usually when the engine is running at its design RPM, which can be reached at usually higher altitudes. But for our consideration, the specific fuel consumption we will consider for both the jet and for both the prop, we're going to consider the specific fuel consumption to be a constant. Okay, so let's examine the specific air range for the jet aircraft, right? So we're going to examine the specific air range for the jet. Okay, so we said that the specific air range is going to be the true airspeed, so the V true airspeed, over the fuel flow for the jet. Okay, so now we'll see that the true airspeed is just going to be the true airspeed. However, the fuel flow for the jet, as you remember, is going to be the specific fuel consumption times the thrust. So we can substitute that into the equation. So it's going to be the true airspeed over the specific fuel consumption times the thrust. Right. And from this equation, again, if we wanted to write it out incomplete, so this is the specific air range for the jet, and is the true airspeed over the specific fuel consumption times the thrust. Okay, so what I want to do with the specific air range is I want to maximize it. Sorry, yeah, I want to maximize this. So the specific air range I want to be maximum. So how do I find the maximum of the specific air range for the jet? Right? I have to find the maximum of the true airspeed over the specific fuel consumption times the thrust. I have to find the maximum of that. We said that the specific fuel consumption we can consider to be an engine consideration, and we also said previously that the specific fuel consumption we will presume to be a constant. I can't find where we said that, but I'm definitely sure that we did. Oh, there it is. So the specific fuel consumption we presume to be a constant. So that basically goes out of the question. So that means, simply speaking, that the specific air range is going to be maximum where the specific fuel consumption is minimum. I think that makes sense. However, I still want to find the true airspeed over thrust maximum. Okay, so interestingly speaking, what we can find is that we're talking usually about cruise condition. So in case of cruise condition, we can see that the thrust is going to equal the drag. So therefore, at this point, I can say, I can substitute in place of the thrust, the drag. Because as we said, it's going to be equal to the thrust required. So I can further take this equation and I can say that 1 over the specific fuel consumption times the true airspeed over the drag maximum. Okay, so I have like two different variables. So how can I maximize the function? Well, from this point of view, this would say that I want the highest true airspeed. I want to maximize the true airspeed to get the highest specific air range, right? Because at the highest straight and level speed that I can achieve, I'm going to get the maximum amount of specific air range, right? So from the true airspeed, I would want the maximum amount. But from the drag, so that would be the Vmax straight and level, right? If I only optimized this part of the equation, right? The drag is also, or the drag is in the denominator of the fraction. So therefore, if I want to maximize the entire fraction, therefore I want to minimize the drag. Which speed does that occur in? At V and D. Okay, so now I have these two conflicting speeds. I have between V and D, which is a fairly low speed, and the Vmax SNL. To basically satisfy or maximize this function. So how can I satisfy both of them at the same time? The answer lies within not optimizing each of the parts of the fraction individually, but optimizing the entire fraction. So what we're doing from now on is we're trying to find the maximum of the true airspeed over the drag. And we're going to do a little trick here, because what we're going to say is that the true airspeed over the drag is maximum, where drag over the true airspeed is minimum. And this is a true assumption. And as you will see graphically in a second, it's going to make sense. Okay, so this is what we're going to be optimizing for. So let's plot the drag curve of the jet. So what we're going to have is on this axis the drag, is thrust required, in other words, or in some literatures. And here we would have the true airspeed. Okay, so we have the drag curve looking something like this. So this would be your drag curve. It's kind of steep, but there you have it. Somewhere approximately here you would have the VMD, and you know where the drag curve meets the thrust curve. At the top, you know, depending on the thrust setting, you would have the Vmax SNL. And it's very definite that the optimum speed is going to be, so V max range, we could see VMR, V max range, is going to be in between these two. But exactly where, right? And so this is what we're going to calculate from right here. So we said that we need to optimize for the drag over the true airspeed. So let's examine that. At any given point, so for example right here, if I pulled like straight to this point, if I connected the origin of the coordinate system and this given point at this given speed, what I see is that the vertical component at this point is basically equal with the drag achieved, right? So this would be the drag achieved at that point. That's what you can read of the vertical axis. So this would be your drag. And the one on the horizontal axis, this one, would be your velocity. Jesus. And this one would be your true airspeed. So what drag over true airspeed gives you, so drag over true airspeed, so this drag over true. Okay, so the drag over the VTAS is going to be the tangent of this angle right here. Let's say it's an alpha angle, the tangent of the alpha angle. So therefore, I want to minimize this angle, or I want to minimize this value. So therefore, in that case, I want to minimize the tangent function. And I can minimize the tangent function if I minimize the alpha angle. So therefore, where is this angle going to reach its minimum? At what speed? At what point exactly? So the correct answer is that there's only one single point where this is minimized, and that would be the tangent of the curve, right? Because at this point you would reach the alpha min, and therefore your drag over VTAS, so this leg right here, is gonna be the least amount, right? Because after this point, at any single point, basically, and you can try this out on multiple points. If I pull the point here, it's visible. It's going to be higher. It's very visible, right? What happens if I pull a straight to the VMD? Not like that. It's bigger. So what happens if I go beyond, or basically to the right of this point? Again, it's going to start getting bigger when I go through it, through all points of the curve. But this one, as you can see here, it's reaching its minimum. And then if it's a If it's a lower one, in that case, it's still gonna be bigger. Right, so this is why you reach the lowest point for the alpha angle, so therefore the tangent, so therefore the drag over the true airspeed, so therefore a maximum amount of true airspeed over the thrust, and this is what we call the VT, or V T over V, which would be the best thrust over weight or over velocity ratio, or just simply VT, which is the 1.32 times VMD. And we're going to say that this is going to be the max range speed for the jet in still air conditions. So therefore the maximum specific air range, right? And this is the caveat for it. So in the tangent for the jet, in the tangent you reach the lowest amount for this angle, for this alpha angle, where the alpha influences the tangent alpha, of course, and the tangent alpha is a drag over the true airspeed, and the drag over the true airspeed influences basically the true airspeed over the drag, which of course influences the specific air range. So where you reach the lowest point for the drag over true airspeed, you reach the highest value for the true airspeed over the thrust over the drag, which reaches the maximum value for the true airspeed over thrust for the specific air range formula, and therefore it's going to maximize the specific air range. So at VT, approximately 1.32 times VMD in tangent. So tangent of drag curve is where you have the specific air range for the jet max, so the highest specific air range. If you fly with a higher or lower speed, this angle is going to get larger, and therefore the tangent is going to get larger, so it's going to get further away from the optimum. Okay, so again, there you have it for the jet. And in the next video, we're going to continue with the best specific air range for the propeller-driven aircraft. So thank you for your attention in this video, and see you guys in the next one.